Thank you all for coming. Of course, everybody that deals with professional speakers always tell you to start the process with a funny line, get people awake and listening. So, story is told of an elderly couple. They're sitting in the back of the church. And the wife leans over and whispers to the husband and says, "Something I ate for breakfast doesn't seem to be agreeing with me. I just had a silent fart, and it's so embarrassing I don't know what to do." The husband leans back over to the wife in a slightly louder voice says, "First, let me help you change the batteries in your hearing aid." Sorry, but it's the only joke I've got with a battery and a punchline. So, but battery failures cause problems, and we're going to talk a little bit about battery failures. So we've got batteries or batteries, and when they go bad on you, bad things happen, and we want to keep them as batteries and try to avoid the batteries. Presentation is kind of jointly done by Energy Standing Content Committee, so we got Lewis here. Lewis grew up off-grid.
I did indeed, yep. So 18 years of my life on battery-based systems before I
How many failures? How many? Too many?
Probably too many to think of, yeah, many.
And we've got Frank Berg that's on the committee with us, and Ken. And let's see, we got anybody else here that snuck in on us? Because I don't know all of them. I met these folks last night when they arrived, because we're on conference calls from across the country, so we don't see each other's face. We don't try not to Skype. All right. If you've got a project that involves photovoltaic other than solar pumping, or any other energy system that's intermittent, including using intermittent grid, which is pretty common in developing worlds, you're going to need some type of energy storage system to make the process work. Batteries are a relatively cheap, inexpensive, and reliable, well, let's say relatively reliable energy storage system. Dollar for dollar for the kilowatt hours that you store, batteries are probably cheaper and more reliable than most other processes that you're going to find that are going to be suitable in the developing world. But the bad part, they can doom your project with high maintenance replacement costs, because if you don't treat those batteries right, they become batteries. And now you got to replace them. You lose your energy storage system, the project doesn't work, the target population is not real happy with what they've got, and then it doesn't work well. So you've got a choice. You're going to treat these things right and get them to do what you want them to do. Decide well. Batteries and renewable energy systems. The simplest imaginable renewable energy system, I've got a photovoltaic panel, I've got a battery, I've got a switch, and a load. And you go, that's a pretty simple system. Is there any system that's that simple? Yeah, there is. Your little key fob got a solar panel, it's got a battery inside, I got a switch, I got a load. It's about as simple as it can be. Probably more simple than anything you're going to be dealing with. Far more likely to see, you're going to see a photovoltaic panel go into a charge controller. That charge controller is going to make sure that the battery gets charged at the proper voltage without the voltage going too high, and also basically hold the solar panel offline until the voltage in the morning gets high enough that we can charge the battery. Notice we got a fuse here for some protection. And then we've got separate terminals for load. The reason the charge controller's got separate terminals for the load is it's got an internal way of disconnecting things if the battery drains too low. How many of you have ever run a battery down on a car trying to crank it? Especially those of you that live in cold climes. I'm in Dallas. Dallas is too cold for me in the winter. I like to see snow on television, and that's it. I grew up in snow up to here when I was a kid. I don't want to see it again like that. So, the charge controller has a low voltage disconnect. When the battery discharges to a certain level, it says, I'm going to protect the battery, your load goes away, which is wonderful for a renewable energy system. It also happens in uninterruptible power supplies in data centers when the battery gets too low and the load goes away. There people complain. You don't think people are going to complain when their load goes away that they've been depending on? They've been listening to the radio and it quit. They had a refrigerator going and it quit. Or worse, you got little kids, the TV's going, it's in the middle of the favorite cartoon and it quits. Yeah, nobody's happy. go to the next one. All right, basic circuits. We have to pitch this because we've got a mix of professionals and students in different disciplines. So some of you will say, I know this, and some of you will say, hey, it's good to know this. Series, if we've got a series circuit, our components are placed literally in series. Each one daisy chains to the next one. In this case, our voltages add across the system. The functional capacity is back to the old chain, the weak link. The weakest link, once you exhaust the weakest link, you're done. So you go, well, what can I do that'll improve that? Well, I can go to parallel here where the voltage is going to be based on, quite honestly, briefly the highest source, but then after that it's going to wind up dragging down. But now the capacities add. So if we look at just half of this diagram, let's imagine these two aren't here. I've got two 6-volt batteries. They're in series, so I've got 12 volts over here. And without this pair that's in parallel, this string that's in parallel, I've got 100 amp hour capacity from these two. You go, each one's got 100 amp hour? Yeah, but I got 6 volts here, 6 volts here. So I get the 12 volts, but until I add this second string, I don't have my full 200 amp hour. So that's how it's going to go in the system. You got series connections, you're going to have parallel connections. Series connections, your voltages add. Parallel connections, you're adding amp hour capacity. Amp hour capacity is just that. How many hours can a battery deliver? How many amps? Straight multiplication. All right, now we've all talked about 12-volt batteries. You've seen them under the hood of your car. Guess what? Each one of those batteries is really a bunch of little batteries inside, because the lead acid battery is really a nominal 2-volt product. I've got a positive plate and a negative plate. The capacity is based on the area of the plate. You go, well, let's make the plates real big. Well, if I make them real big, it's like wallpaper. Now my battery is 1/2 inch thick and it's the size of the room. That don't fit in the car. So they make the plates where they'll intermesh with each other. I've got positive plates and negative plates. I've got a little separator between them. So I've got multiple positive plates, multiple negative plates, and they're all welded together to internal connections. And so inside each cell, 2-volt cell, is really a set of parallel sets of plates that are ganged together. So the 12-volt battery is 6 2-volt cells, nominal 2 volts. It's really about 2.25 volts a cell, thereabouts at fully charged, depending on the manufacturer, how their chemistry on the plates is. So inside that 12-volt battery, I've got 6 individual cells that are all connected in series. And I've only got 2 points, positive and negative points, that I can check voltage at, or I can make an external connection to my load. Well, what happens if one of those cells in there gets sick? The whole battery voltage that you see sags down, but there's nothing you can do to fix it because it's inside a sealed block. So we've got 6 nominal 2-volt cells connected in series, and that's our 12-volt battery. Fully charged, about 2.2, 2.25 volts, so around 13.2 volts. All right, so we've got our photovoltaic panel feeding our 12-volt battery. We stick the meter in there. We expect to see, if the panel's in the sun, somewhere a little above 13.2 because the battery's hopefully charging. Hopefully not much more than about 14.6, 14.7, again, depending upon the manufacturer, the exact chemical mix that they've used on their plates. And that's going to be charging our battery. Next. All right, we've got the same situation here, but in this case, internal in there, our series connection had a corrosion because the connections between the cells are made out of lead that's poured, and when that lead is molten lead is poured, it crystallizes. And sometimes you get what's called intergranular corrosion, or you just get massive corrosion, and the straps between the cells break down. Now I've got an open right there. What's the meter going to read? In this case, the meter is going to read whatever that photovoltaic panel is putting out open circuit. So it may read 17 volts. And you go, hey, I've got a 17-volt battery rather than a 12-volt battery. No, you got no battery. You got a battery, not a battery. So if you've got charge source or other batteries that are in a parallel string with your battery, you're going to have to lift the leads to that battery to really tell what's going on internal. Because if there's a solar panel or another string in parallel, they're going to hold the battery up. This thing will look like a capacitor. Just 2 open plates, It's got charge across it. You'll read 12 volts, 14 volts, whatever. You know, depends on the panel or depends on what the other, if you got a charge controller in there, it may very well show 13.6 and you think you got a great battery. You don't. So in doing maintenance, there's times where you're going to have to lift a battery lead to tell what that battery is really giving you. Find the problem, you're going to have to lift the lead. Okay, we'll talk about safety in a minute, but 12-volt batteries, short of doing really stupid things with them, 12-volt battery isn't going to cause you a shock hazard, so don't worry about those. All right, if we're going to talk about battery maintenance, we have to recognize the different types of batteries you may encounter. Most common, most economical, most widely available is our wonderful flooded product. We got one here with a clear case where you can actually see the plates. These are always vented batteries. Venting means that as we put power into the battery, some of the power is used to break the water in the electrolyte down. The electrolyte is on these batteries is water and sulfuric acid, about 1.22, 1.25 specific gravity, so it's really stout acid. You want to buy a new pair of jeans, let some of this acid drip on your jeans, and you'll get a brand new pair of jeans, depending on the size of the hole and where the hole is visible. Some of the electricity going into that battery is going to break that water down into hydrogen and oxygen, and those gases tend to wander off, especially the hydrogen being lighter than air, it wanders off if it's got a way to vent. If you install one of these batteries, make sure you're in a good vented compartment. Don't put this thing in a sealed box, because what you're creating is a nice hydrogen-oxygen mix, and hydrogen is one of those wonderful gases along with acetylene that's got an explosive range of about 4% to 96% in air. Anywhere inside there, it'll ignite, and when it ignites, you remember the little pictures of the Hindenburg? That's a slow one in comparison to what can happen. I can show you pictures of a data center in California that literally lost the roof. It blew off. So they're going to require replacement of water. So these are caps that can be unscrewed to get into each of the individual 6 cells to check the fluid level. You've got, because these are open vented to the atmosphere, you've got a risk of some acid vapor mist coming out. You've also got a risk of corrosion at the terminals because they're in an acid environment. And you've also got a wonderful problem of conductive tracking because the battery electrolyte is electrically conductive. When it collects, you know, from a leak or from venting of one of these cells, it can be conductive. And in this case, we've got a wonderful developing Marolles situation. It's sitting on a board or a piece of tile. Oftentimes these will be on a metal rack. Depending on the situation, that metal rack may or not be tied into an electrical ground of the system. Quite honestly, on low voltage systems, it's better to let the thing float where the batteries aren't tied to the ground of the frame for the batteries. But if you get a conductive path from that battery to the battery frame and the system is grounded, now I've got a small internal short. Now it's not really a short, it's a high resistance connection in the middle of the battery string. So I've got a loop that's going to self-discharge parts of the battery string, and other parts of the battery string don't discharge. Batteries don't like to be unequally yoked with batteries that aren't charged to the same level, do they?
Not at all.
They find this objectionable, and they become badderies. So we don't want to let this happen. So you always want to check and see and clean the tops of these batteries and make sure you don't get a conductive path to ground that shorts out part of, gives you a leakage current. All right, let's go. Flooded batteries, these are batteries here. Okay, you see that nice green? Anybody know what color copper turns and when you get corrosion? Yep, that's it. These were in Haiti. This was backing up a little UPS system for all of the internet and telecommunications for a facility. And these were sitting out exposed and they were corroding. When you see the tops of the batteries like that, you can figure you've had some electrolyte loss, or else when they watered the batteries, they overwatered the batteries and spilled it everywhere, didn't clean them. Here we're looking in, we pulled the tops off. I did a bad thing here. Notice I didn't get rid of that loose corrosion. I should have. If that gets down into the electrolyte cell, not good. So when you pop these covers, make sure you try to sweep the corrosion away. In this particular case, I was doing a survey. I didn't have anything else with me. I was careful as could be, and didn't drop any in. But at middle cell, the electrolyte level is low. If you can see the plates, that's bad. Get some water in there. Because if these plates stay dry, you have a lead sulfate that crystallizes, and it's non-reversible. And you've just lost surface area on those plates that's usable to giving you capacity. Down at the bottom here, this is a wonderful UPS string. 540 volt DC with lots and lots of little jars. Fortunately, our projects, you're not going to have that kind of voltage, most likely. You can in other systems. So if you ever hit a high voltage system, be aware. This particular one's on the earlier UPSs, these are floating. There is no tie between frame ground of this battery string and that supports this battery string and the electrical components of the battery string. That battery's sitting there floating like an island. So as long as it's floating like an island, you can literally walk up and touch any point on that battery system, even on the terminals, and there's no current's going to flow through you because there's no place for that current to get back to the other side of the battery. But you get one of those electrolyte leagues or a conductive path that hits that frame ground, and now I may have a connection back over here to the frame ground, which means for every cell I've got 2.2 volts, and all of a sudden at this end I may have 180 volts, and on the other side I may have 300 and something volts to ground when it was supposed to be floating. So always check your battery terminal voltage to local frame ground and see if you've got a grounded system or ungrounded system or an inadvertently grounded system. Over here we've got a jar with flooded jar, and this one just had electrolyte level is there. There's our minimum, there's our maximum. This tells us nobody has been watering this jar in quite a while. Okay, water. Where are you going to get water for these things? Ideally you want distilled water. Everybody remember seeing the distilled water in the store at the last developing country you did a project in? No, okay, you go, how about bottled water? Well, it sort of depends. There are minerals in groundwater in certain areas that are bad for the batteries. There are other places where the groundwater would be perfectly fine to put in the batteries. You decide, you got to find out. If you're in a place that's got high total dissolved solids, certain minerals, calciums, other things, not good. So you got to find out. In a jam, where could you get water that's better? Well, if you're staying someplace that's got air conditioning and you can find where the condensate comes off the air conditioning, that's essentially distilled water. Tap that source. That you go, well, I'm not staying in an air-conditioned hotel anymore. Well, you know. How about melted frost out of a refrigerator? But again, you're in a developing country village that is on a renewable energy system. You probably don't have a refrigerator. Probably don't have a freezer to tap frost. So just be aware, do some checks on your local groundwater before you take. Now, rainwater and a roof catchment system is probably going to give you clean enough water. Go ahead. You got anything? Chime in.
I sure will, yep. So this, however, is more commonly what you will see as a sealed lead acid battery in a developing world context. So these are sold as maintenance-free, which means you can't do maintenance on them, even if you'd like to. And what this means is that it's a sealed vessel, and under a severe overcharge, it will actually vent hydrogen as it overcharges. So this can actually present some serious problems because you actually are losing electrolyte levels, and there's no way for you to open this up and recharge those electrolyte levels. So what does that mean? That means that you don't overcharge sealed lead acid batteries. So you have to be very cognizant of your charge controller settings and making sure that you're going to charge it a little differently in terms of voltages and times than you would a standard lead acid battery.
The manufacturers are always going to provide you for their individual battery with the recommended charge levels. Pay attention to them, follow them. If you've got a good charge controller, a lot of those are going to have a temperature compensation probe. Put that probe on these sealed batteries. Don't put it on the outside where you get the best airflow. Put it between the batteries where it's confined, where you actually get a better shot at measuring the temperature of the battery rather than, you know, out open air. Because those charge controllers are going to back down the charge voltage as those batteries get warmer, which prevents other problems we'll talk about. Lead acid batteries are happiest at 25 degrees C, 77F. How many of you have had an EWB project where the average ambient temperature was 77 degrees and it stayed that way all the time? Nobody did anything in San Diego? Oh, that's a shame. The problem is, if you take any lead acid product and you warm it up 10 degrees C, you've cut the life expectancy in half. Oops. There went our 5-year maintenance agreement plan out the window. So these are some big sealed lead acid. They look like standard 12-volt batteries. This is a 24-volt start system for a diesel engine. But these are labeled maintenance-free, sealed. So there's no vent ports that you can get to.
What happens if those leak?
Pardon?
What happens if they leak?
When they leak, as he said, the electrolyte level goes down and it is irreplaceable on most of these. Eventually you're going to have to trash it. You've lost capacity because you've got less acid. You're going to have plates that sulfate, crystallize, and lower the available surface area. So you're losing amp hour capacity. Let's go ahead. Other examples of sealed lead acid product. These little 12-volt jar, and you go, well, that looks pretty good. Yeah, that's in a high voltage UPS. But what we've got right here, I've got a big lug and a small battery terminal. Now, in electrical systems, you generally figure 1 square inch of copper will let you flow 1,000 amps through it. Now, when you're dealing with a lead-plated product, okay, be charitable, cut it back a bit, but we're dealing with a battery post here that's maybe 5/8 of an inch in diameter, circular, and this particular string was designed where 300 to 400 amps had to go through that battery string. That's not enough conductive area. Those posts will get hot, real fast. So look at what you're doing in the design. Look at what you're doing in real life. If you've got corrosion, you're reducing the contact area. If you've got a high discharge ampacity, that connection is going to get hot. That's not a good thing. It gets hot, the metals expand, we get a gap, things cool off, we've got room for additional corrosion materials to get into that connection. Over here, those look like they're flooded lead acid product. And from the picture, I would have assumed they were flooded. But when you zoom in, they're actually sealed. Those are vents, valved vents, and they will release under pressure, but they're not removable to service the battery. Down here, these are 2-volt sealed cell. Well, semi-sealed, you see that? That tells me the seal wasn't too successful. The jar to cover seal probably leaked here. These are in a telecommunications plant. These batteries are about 12 inches square. They're about 30 inches deep, 1,400 amp hour at 2 volts. So you can go to the next.
Did you say square inch is 1,000 or 100?
1,000 amps a square inch of copper for bus bar wiring is the generally accepted, design rule of thumb. Deep cycle. Deep cycle is not a different battery, well, it's a different battery construction, but it's the same lead acid product, the same plates and all. They just make the plates a little thicker and they design the battery to have a deeper discharge. Your car battery, if you pull more than about 30% out of of the rated capacity out of a car battery, you're knocking its life cycle down quite a bit. So you want to be gentle on these things. Just because a battery says it's good for 100 amp hour, you don't get to use the whole 100 amp hour. It's not like your car tank, you can drive it till the little light flashes and says, you really better find a filling station quick here. Don't treat that with your batteries that way because they won't live long. But anything that's labeled deep cycle, at least the manufacturer is going to claim that he designed that battery to handle a deeper cycle. So a deep cycle product, you can probably get about 60% of the rated capacity out of. Now, you design it in the States for this site, and EWB says we're going to buy all our products locally, in country. Finding a deep cycle rated product in a developing country may be a challenge. And even if you do find it, what's going to happen in 3 to 5 years when that battery has to be replaced? Where are they? What are they going to do? They're going to go, I want a battery like this. And they're going to carry one to the store. I need 4 of these. And they're going to say, 12-volt battery, car battery, and I'm going to hand them 4 car batteries. Okay, now all of a sudden you're designed for a 60% depth of discharge on a 100 amp hour deep cycle battery, has been replaced by a same size, looks the same, but it's a standard auto battery that you can only get about a 30% depth of discharge, and the whole system design is now different, and the second batch of batteries aren't going to last as long as the first batch lasted. So just because it looks the same doesn't mean it is the same. Let's go ahead.
So I want to chime in one thing on the deep cycle,
Yes.
which I think we're going to get to some plates later, but the way that you tell if it's deep cycle is how heavy is it and how thick those plates are. So I think we'll be talking about that as well a little later.
If you were to just compare the weight of a car battery and a deep cycle battery that looks the same physical size, the deep cycle battery is going to be heavier. The plates are thicker. It's beefier built internally. Otherwise, the outside of the battery, they're standard frame size. Excuse me. All right, I'm going to mention these just because you may encounter them. You probably won't, but if you do, you need to know the difference. These are a pocket plate NiCad. These are a flooded nickel cadmium battery, not like the little sealed consumer grade AA's, AAA's NiCad batteries that are dry. This is a liquid filled battery. However, this is a potassium hydroxide, and it's a real stout alkaline. So just like we said, be cautious of the acid battery, be cautious of the alkaline battery, because it'll eat holes in you the other way. Either way, you're going to wind up with trouble, especially if you get it in your eyes. This is a serious eye wash problem for both types of products. The battery electrolyte is bad news in your face. The way you're going to tell these batteries apart from a lead acid battery, A, you're probably going to see something on the label that says NiCad. B, NiCad products are always a nominal 1.2 volt. So if you're reading a battery and you kind of see from the molding on the side of it how many cells are in it, and you go, hey, that's only about 1.2 volts a cell. Ah, it's a NiCad battery, so I've got an alkaline electrolyte rather than an acid electrolyte. Always use a separate hydrometer from one that's been used on a lead acid product, because the acid residue will contaminate the alkaline, and the alkaline residue will contaminate the acid. You will wind up killing whichever battery you go to next, so keep a separate one. Again, there are some things you can do on these for maintenance, which we'll talk about, but it's basically keeping connections clean, keeping the tops of the batteries clean. These you're going to clean with maybe a vinegar water solution, whereas the lead acid battery you're going to clean with a baking soda water solution. Be careful with the baking soda water solution not to get it inside the electrolyte. Same way here. Make sure the caps are on when you're cleaning them. How to read a battery label. Okay, because these manufacturers provide you with a lot of information, they also don't provide you with a lot of information on the battery label. You may have to go to the catalog to get the information you want. Nominal voltage, why is that important? Well, we want to know how many cells are in here. SOC. SOC is state of charge. That's information about where you can find information on how much capacity is left in that battery. Are you going to be basing on voltage? If it's a sealed product, you may be able to base it on specific gravity if it's a flooded product. Temperature issues. What's this battery rated for on temperature issues? What temperatures you can store it at? Capacity. How many amp hours, how many watt hours does this battery have? In this particular case, this is a Chinese-made high-rate UPS battery. And the label up here, H12V100/A. And you go, that looks like a 100 amp hour battery. Well, it looks like it, but the marketing people are like marketing people everywhere. They try to sell more product than they got. Look right below it says 100 watts per cell, and there'll be a time here that I can't read this one, and it's at 25 degrees C. So it's 100 watts per cell, so we immediately got to divide that 100 watts by 12. So this is about an 8 amp battery for 15 minutes. Now, some of them are only rated for 5 minutes. And you go, wait a second, the battery's only good for 5 minutes? Yeah, at that rate, it's only good for 5 minutes. So capacity is always going to be at a given rate of hours. And if you go less than that rate of hours, you won't get the full capacity out of it. The electrolyte stratifies inside. In the telephone industry, we typically use 3,900, 4,000 amp hour product. That's at an 8-hour rating. We said, we're only going to burn this battery down in 4 hours. We're going to use it quick. Manufacturer says, well, you get maybe 80% of that in 4 hours. The typical deep cycle car style battery is rated at a 20-hour rate. So you buy a 100 amp hour battery, It's rated at a 20-hour rate, so you get 5 amps an hour out of it for 20 hours. You go, well, my design says I'm going to pull that battery down in 10 hours. You're not going to get 100 amp hours out of it. You may get 80 amp hours out of it. That's total capacity, and then you only get to use 60% of that, remember. So things go away quick. So always with the capacity is what was the rated discharge time. You've got to look at that, got to keep that in mind. Some batteries will have charge rates. How fast can you safely recharge that battery, especially the seal batteries, so they don't overheat, they don't go into other problems. Go next. Battery labels. Sometimes the battery labels give you useful information. Sometimes they give you information that may not be so useful. We'll start here at the bottom. This is a sealed product, basically a car battery, and the manufacturer proudly proclaims wonderful things here. He gives you a part number, 24. It's a 12-volt battery. Marketing people again. It's actually a group 24. We've got CA at 32F up here of 500. CA is cranking amps. That's how many amps this battery will dump to the starter to turn your car engine over when you're in Duluth, Minnesota in January. And it warmed up to 32 degrees in Duluth, because most of the time it ain't. So it'll give you 500 amps. Well, that tells you absolutely nothing for your renewable energy project. Nothing, because you're never going to try to short that battery out into a 500 amp discharge. Okay, down here I got CCA at 0F, 400 amps. Okay, if you chill that battery down from 32 to 0, you've lost 20% of the amps that it could dump on you. And you go, I'm still not going to get it that cold. I'm in Cameroon, it's 85 degrees on a cool day. So that's a useless number. That's a useless number. Here's one that's closer to useful, but still not terribly useful, RC. RC is reserve capacity. How many minutes this battery will support a 25 amp discharge? And they pick a 25 amp discharge, I guess, because that's about what a trolling motor draws, and these are batteries used in RVs and trolling motors on bass boats. So it'll run your trolling motor for an hour and 140 minutes, which will get you way out on the bayou and won't get you back to the dock. But that's your problem. It's a battery again. So this label gives you, a lot of information, but the information may not be terribly useful. You've got to go to the battery manufacturer's catalog to get some useful information, quite honestly, a lot of times. Okay, up here I've got a telecommunications sealed product. It's got this nice trash can with the X through it. It says don't throw it in the trash can. This particular battery weighs about 200, 250 pounds. There's another reason not to throw it in a trash can, called a hernia. It says on the capacity rating up here that I've got 1,400 amp hours at an 8-hour rate, and that's to discharge this battery down to 1.75 volts a cell, which is about as low as in an emergency you want to take one of these. So I got 1,400 amp hours, and it helpfully, but not terribly usefully, says I get 1,400, and it's either 30 or 1,450 on a 10-hour discharge rate down to 1.8. So this gives you a clue of what kind of capacity you could get, but again, you don't get to use all the gas in the tank. Other things, float voltage, it says you want to float this battery at 2.25 plus or minus 1% volt per cell at 25 or 20 C. And you go, it ain't that cold where I am. Well, then go back to the manufacturer's catalog and find out what the volt per cell needs to be at the temperature you're likely to encounter. Right. Okay, state of charge. What's the approximate percent of the residual capacity left in the battery? This is a typical chart I grabbed from one manufacturer. Do not apply this to any other battery without the manufacturer's permission, because they're all different. Functional life on a battery is considered when the battery can no longer provide more than 80% of its initial rating. So now you go, well, if I design my project right, I can use that battery when it's below 80% of its original capacity. And so you might have a longer number of cycles, a longer number of life based on how you design the system. But when they're defining the expected number of cycles, it's based on this. When the battery only has 80% of its original rated capacity left. So state of charge, how full is the gas tank, if you will. That can be estimated by battery voltage on this chart. It can be better estimated by the specific gravity. If it's a flooded cell that you can actually get in with a hydrometer and measure the specific gravity of the electrolyte. Now, this is a fun one. Expected number of cycles. Now, this is in particular for a particular gel cell product. If you use the battery and only use 10% of its rated capacity, this manufacturer says you get 5,700 discharge charge cycles. Okay, if we do a discharge charge cycle once a day, that's a pretty long life. That's a great battery for that use. But that means you're buying an awful lot of batteries if you're only using 10% of the rated capacity. You go, well, if I'm using 25%, okay, all of a sudden I'm only getting 2,100 discharge charge cycles. And you go, I'm still buying a lot of batteries because I'm only using a quarter of what I bought. I bought a 100 amp hour battery, I only get to use 25 amp hours. This ain't real good. I want to use half of it. Well, okay, if you use half of it, you're only going to get 1,000 cycles out of it. 1,000 cycles sounds like you're going to be back there in 3 years replacing that battery. But what happens if bad things happen and somebody bypasses the low voltage disconnect, or they leave the switch on overnight and they use a little more capacity of the battery than you intended for them to use? Okay, you use 75% of the battery, now you get 650 charge cycles. So less than 2 years, you've got a battery that's dead. And you go, well, I got a 5-year commitment to the village. You got a problem here. Real quick. Go ahead. All right, low voltage disconnects. Remember I talked about a low voltage disconnect and a charge controller. If you don't have a charge controller, make sure you got a low voltage disconnect somewhere in your system. Something that says, that battery, you've used all I want you to use of that battery. I'm not going to let you drain it any lower than that percent load. Saving batteries everywhere from too deep a discharge. It's going to disconnect the battery, to disconnect the load to save the battery. It's built into the better charge controllers. The way you can tell, if you've got separate load terminals from separate battery terminals on the charge controller, it's probably got a low voltage disconnect built in it. Some of them are programmable or tweaker pot adjust, so check with the manufacturer the literature on your charge controller and see where you're going to adjust it and calibrate the thing.
Yeah. If they're not adjustable, you'll often find that they're very low. They're going to be barely protect the battery, but you're still going to be able to deficit cycle
You're going to be at a
over time.
75% discharge or more.
You're going to have reduced life if you're hitting that on a default on most charge controllers.
So if you're in system design, now granted this is operation and maintenance, but if you're in system design, make sure you get a charge controller where you can set that protection voltage high enough that you get some life out of the batteries.
And when we have a system that's not as simple as the module, battery, charge controller, and lights, you're going to have other strategies for controlling that low voltage disconnect through controls, inverters, or other separate controls. So
yeah, a lot of the inverters will have a low voltage protection for the inverter where it says, I'm not going to take a voltage that low because I would have to take too many amps and my wire inside's only so big, so I'll reject the low voltage. And the inverter just shuts down to protect itself.
Ready?
Yeah. All right, battery safety. This will get your attention. This was a UPS string, 540 volt DC, large flooded cells. The contractor is cutting a battery cable with a pair of wire cutters, basically like a pair of limb loppers. 2.5 foot leverage to cut the wire. The wire was either 500 or 750 kmcm. So this wire is twice the size of your thumb in diameter and designed to carry, well, let's see, if it's 500, that's 400 and some odd amps. If it's 750, it's about 600 amps that it's designed to carry. Well, when he cut it, the wire's pretty stiff when it's that big, and when he cut it, it snapped back. And in this case, it snapped back into these copper bus bar. And if you notice a small problem with the copper bus bar, they did not go to see a dentist. That gap is vaporized. The bottom one is a 6-inch by 1/4-inch thick copper bus. The upper two were 1/4-inch by 2-inch copper bus. The missing copper is vaporized. Briefly, this was, 540 volts at probably 5,000 amps. We're talking 2.5 megawatts for a few split seconds. Yeah, this will light you up, quite literally. If you notice the circuit breaker down in the bottom, what happened to the Bakelite? Nice and toasty. This will literally catch you on fire. So working with battery systems, realize the voltage may not be that high on a 12, 24, 48 volt system, but if a short, a fault occurs, you can get an incredible number of amps flowing. Battery won't shock you. You can reach across a 48 volt system, touch it barehanded, you won't feel anything, go about your business. But if you get it faulted with something conductive, you're going to vaporize metal. When that metal is vaporized metal and human tissue are a poor mix. Don't try it. Bad. Notice a little fluke meter down in the bottom of the breaker can there. So yeah, pay attention to what you're doing. Let's go to the next one. Flooded battery maintenance. We're showing one type of hydrometer here. I picked up one this week at a renewable energy store up in Pennsylvania that's got a little tilting. Use a hydrometer. Hey, you got to have a flooded battery. You got to have access to the port. We're going to pop that cover, check the electrolyte level. If you add water, don't check with a hydrometer because you just added water. The sulfuric acid is heavier than water. You add water to the top. You give the battery about a week for that thing to mix. If you just pour water in it and try to read it, you're going to read the water. You go, oh, it's real bad. It's real low. No, you just put water in the top and it floats on top of the acid. So you're going to squeeze the bulb, put it into the electrolyte, draw a sample in, take a reading, put it back in the same cell, squeeze it out, rinse the hydrometer out, go to your next one. In this case, we've got a vertical, and you read it at the fluid level if you've got a float type one like this. Be cautious. A lot of times this hydrometer gets hung up back in the room where the battery is. Some of them will put a little, like a glass test tube or something down here to catch what drips out later. Well, what drips out later is battery electrolyte, sulfuric acid. Water will evaporate until that is extremely concentrated. So what drips out sits in a little jar, a little more water evaporates out of it just from vapor pressure, and you get really concentrated acid. This is a reflectometer.
Yeah,
refractometer.
Refractometer. So this is a calibrated refractometer. It's a little more expensive, around $100 or so maybe not a developing world tool. The nice thing about it is you're taking a very small sample of electrolyte out of the battery, so your potential for contamination is less, and you also have a little more accuracy depending on the hydrometer. Something like this, it's hard to get this down to the 0.01 hundredth or less. With a refractometer, you can actually really see those specific gravities a little more closely. So the easiest way is just to have a little standard pipette, take 1 to 2 drops, place it on there. It's actually refracts that through the tool. It's self-calibrating, and you read your specific gravity directly off the tool.
So flooded battery maintenance, you want to remember safety. You're going to be checking cell voltage. You're going to be checking specific gravity to give you an estimate on state of charge, cleaning connections. You're going to clean them with a baking soda water mix. If you got corrosion, you might have to break that connection apart, clean it down to bare metal, put it back together, reconnect it, retorque it to the manufacturer's spec, coat it with some kind of grease. Vaseline will work. No oxide is a little better, but Vaseline will work. You can get that pretty well everywhere. Check your electrolyte levels are okay. And as we said, grease connections. You've got to speed up a little here.
Yep.
Okay, here's a good example of, this is corrosion. I think everybody would recognize that. Again, the cell we showed with the low electrolyte level. Sealed battery maintenance. Well, you just said sealed batteries couldn't be maintained. Well, inside the sealed battery, the sealed part can't be maintained, but the outside part you can. So what do we got? We've got connection issues again that we've got to look, and this is some no oxide on them. And this is a UPS string, again 540 volt DC. What do you notice with the technician checking voltages? No face shield. Yeah, and he's pushing voltage probes all the way back here. You short something out, that sealed battery may not stay sealed. It may decompose rapidly and throw pieces at you. So, yeah, just because it's a sealed battery doesn't mean it has to stay sealed. So, safety. Cell voltage, because that's all you're going to be able to tell about these cells. So you're going to be estimating state of charge based on cell voltage. Cleaning connections, greasing connections, anything of this sound familiar? Temperature issues, you're going to make sure these batteries stay cool. that you don't see evidence of leaking or evidence of outgassing. Pocket plate NiCads, again, these are flooded batteries, so you can do a hydrometer reading, different hydrometer. Remember, it's 1.2 volts per cell, so all your voltages in your state of charge comes from a different catalog. How batteries die? Well, they die sometimes of old age, which you really like, but more often they die of neglect, and all too often benign neglect, which isn't so benign. You can have corrosion issues, internal and external corrosion issues. You can have sulfation. If you let these batteries stay in a discharge state, they'll start sulfating. Once sulfation is normally considered an irreversible process. There are plenty of marketing people that will sell a product to you that is guaranteed to desulfate your batteries. What kind of luck have you seen with them?
Very little.
Yeah, it's a great marketing tool. You haven't seen any better luck with it, have you? Okay, plenty of people will sell you something that'll desulfate your batteries and bring them back to full capacity. Don't waste your money. Plate shed. These plates flake off parts of them, and hopefully this stuff falls to the bottom. Well, if it falls to the bottom and collects, I might get a short between my positive and negative plates, and I start losing battery capacity. Thermal runaway, that's the bad one. If you let, especially the sealed products, if you let them get too hot and the voltage too high, they can get into a vicious cycle where the battery warms up, and as it warms up, it creates additional internal heat from the charge voltage coming at it, and it gets hotter inside, and the hotter it gets, the more internal resistance goes up, and this vicious cycle results in, A, the batteries vent, and you walk into the room and you think, there's 100,000 rotten eggs in here. Hydrogen sulfide. You've toasted the batteries. I've come in and found sealed product with the battery skin over 130 degrees. That's a bad thing. In this case, there were some wet cells that got into a thermal runaway, and a lot of the manufacturers will tell you wet cells can't do a thermal runaway. Oh, yes, they can. Been there, done that. The t-shirt's got holes in it, but bad things happen to otherwise good batteries. Thermal runaway, high temperature, from a high discharge rate or a high recharge rate. You got to prevent it. There is no cure after it's occurred, so you got to prevent it. It destroys the battery. See this wonderful GU45 here, 3,900 amp hours, 2 volts. This thing looks like it's about to give birth to a litter of AAAs. I assure you it is not. Normally that battery case is straight. This one got hot. These tops normally are nice and flat. They're not bulged like this. Thermal runaways in a sealed product. Sometimes they'll actually rupture the case. You can see these bowed out here. This was a set of batteries that got discharged pretty deeply when they shouldn't have. These weren't all that far from here. Okay, the batteries died. Who's going to take care of the dead? Went through Cambodia years ago, and every house we drove by on the main road, through the front door, which was a piece of cloth hanging, you could see a little glow of about a 5 to a 7-inch black and white TV powered off a motorcycle battery. And you'd see people pedaling the bicycle going to town with one of these motorcycle batteries strung on it. And in town, there's a little diesel generator and 87 sets of jumper cables, tiny little alligator clip jumper cables in a rack. And the guy was in the business, and when he had 6 or 8 batteries that people had brought when they came to town, came to the store, he'd hook all the batteries up, crank his generator up, and recharge the batteries and send them home. There's no low voltage disconnect till the TV picture goes and shrinks down to a dot. What's going to happen after that battery can't hold a charge anymore? I know what's going to happen. It's going to get pitched in a rice paddy in the backyard. Who wants to eat rice that's grown in a rice paddy that's filled with lead acid batteries? Yeah, I don't get any volunteers here either. So, lead acid batteries are highly recyclable in the developed world. Like 98% of that battery can be recycled. What happens where you are? That's a good, we create a potential environmental problem in the future because we've got heavy metals, we've got acid residue, we've got plastic waste. Who's going to be there to take care of the dead? If you put a system in, make sure that you've taken care of the end-of-life issues.
What do you suggest?
Well, that's where we get into a discussion here, but let me cover this real quick. This is the full battery maintenance inspection checklist that's on our blog posting back in oh, was it that early? Was it April? We're still working on getting the final document peer reviewed where we can get it out because it's going to be 30-something pages, but it's far more than just a maintenance checklist.
And if you've signed up on the sign-in sheet that went around and checked, received more information, we'll send that out once we get a final version, and we'll send out a link to this existing pieces as well. So.
And you'll have a chance at the end to sign in if you missed it earlier. Okay, we've got hopefully a little time for questions. How much time we have left?
We got about 9 minutes, right?
Ah, okay, quick questions. Okay, how do you take care of that future battery, the battery died issue? If you're going to put batteries in a system in a developing country, you got to let people know that when this thing is dead, you can't just throw it in the backyard. Fortunately, the lead is valuable. Lead's pushing close to $2 a pound right now. So there's some salvage value in that lead. And that battery's probably 40, 50 pounds, so that's pretty good salvage value. So let people know, so-and-so in the capital city, so-and-so in this area. Do the research because, we keep talking about sustainability and we've got to think about that when we're putting a battery system out there. What's going to be really sustainable in the future? We want to make the system as sustainable as we can, but there are components of it that do have end-of-life issues, and it's our responsibility because we put it there to make sure somebody's taking care of it at the end.
The better relationship you have with your local contractors and suppliers, the more likely you have that strong connection between community and suppliers.
Yep.
It's going to be a lot more likely that they're going to want that battery back as a core refund for the next set of batteries.
It can help pay for the next set of batteries.
Can they be refurbished or are they just recycled?
They're really not refurbishable in developing world conditions. Years ago, when I was with the Bell System, I did a survey on a battery breaker in Louisiana, and the guy that was with me from Birmingham lost a pair of shoes because the acid running on the ground ate the leather soles out of his shoes. I have seen one battery breaker in a developing country, and basically the lot that they had rented a lot with a tin shed. They did battery breaking of valve-regulated product from cell sites, and the site was contaminated. The next people that came along that wanted to use it, that were asking me about it, was going to be a preschool. Yeah, I said, you're going to have to scrape about 6 inches of soil off and get rid of it somewhere to do this thing. And that was just 6 inches. I didn't have anything with me to test for lead, but I could tell there was lead all over the place. So, yeah, developing world situation is totally different kettle of fish on what happens on these batteries. It's cheaper.
Yep.
Lithium polymer, yeah, there's all kinds of wonderful battery chemistry that are coming. Try to buy it in Uganda. Buy one in Malawi. If you want to see some interesting video on lithium polymer, if you've flown lately, they'll tell you, you can't put lithium batteries in your checked luggage. If you ever want to see why, go to YouTube and do a quick search for lithium batteries rifle fire. There are people that have taken laptop batteries and set them up at a target, shoot it with a rifle, and in some cases they're shooting it just with an air rifle. And you should see the fire starting capability of a charged lithium battery when it gets damaged. It is incredible. You've seen some of those videos.
I have indeed.
They are impressive. You go, I've literally seen one where a guy took a cell phone battery. Well, it was an RV aircraft battery. And he had a little pivoting arm with a hammer. And he whacks it with a hammer while the video's going. And inside 30 seconds, there's flames shooting out. Big time flames. And you go, maybe I should carry a lithium battery with me as a fire starter when I go camping. Whack it with a rock and jump back.
What did you say to clean leads of NiCad batteries with?
NiCad batteries, you're going to want to use a mild acid solution. Probably vinegar is going to be the easiest one you're going to get. Easiest and safest. Yeah, you could use sulfuric acid or nitric acid, but you shouldn't.
Thinking a solar panel running small water pump, can it do without any battery?
Yes.
Yes.
If you've got storage in a system like that, but it's not battery storage. You want to store water. And you want to store water at an elevated spot so that whenever the sun is out, the pump is pumping. why store it in a battery and lose 10 to 15% with the battery storage? Because the battery doesn't give you 100% of what you put in it back. You're going to get 85, 90% at best back. So why do that when let the pump run, store the water in the tank. It's there overnight. Far more efficient that way. Far smarter, and you don't have to buy the heavy battery. You don't have to spend the money. Water tanks are cheap compared to batteries.
Yep.
Real cheap compared to batteries.
Especially for ongoing maintenance costs.
Yeah. And you just solved a future problem. You don't have to worry about a dead battery later on.
I was wondering, the final document that you're going to send out, are you going to have kind of an interpretation guide to go over with community members? Because this is some pretty hardcore science.
Unfortunately, the document is pretty hardcore science, but the checklist is not, can be translated and, put at a level that people can understand it. The checklist, the rest of the document, some of it's pretty heavy. Any other questions?
Aren't the solar panels just as environmentally messy?
Not for most silicon crystalline. So there certainly are chemistries like cadmium telluride that have issues, but for most of what's in the developing world, it's pretty well standard. It's not any worse than your cell phone or anything else with a semiconductor chip in it.
Yeah, there's some additives to the silicon, but they're tiny percentage.
Very
so
small doping.
It's
yeah.
electron doping, so.
Yeah. Frank.
One thing that comes up is the batteries will need to be replaced. We talked about kind of creating contact and kind of support network for when that happens. What about financially to replace batteries? Anything you guys have seen on programs setting aside like a funding source or collecting fees?
Sure. I mean, my feeling certainly is every project should be setting aside funding for maintenance. There's no real maintenance-free systems that we do, and especially any battery-based systems. Yeah, you got to have that conversation up front and in depth with your communities that having these systems is not an initial cost or contribution. They need to support those maintenance costs for the long term. So
Even solar water pumping is going to have some maintenance because you're going to have to clean the panels periodically. You're going to have to, clean the tanks. You're going to have
pumps don't last forever.
Yeah.
Yeah.
If it's made by man, it doesn't last forever. If you don't believe me, go talk to the NASA folks.
In your experience, I mean, is there an optimum life design for a battery? I mean, it's discharge versus time. But in the developing world, you got the cost of capital, you got the replacement cost, you got the. So,
Sure.
I mean, is there a practical rule of thumb that you guys have found so far?
It really depends on
How
what
you treat
chemistry
'em.
you can find, and it's very site-specific and resource-specific. There's
you
certainly
over-
some work.
If you
being done
over
in those
discharge
areas.
that battery and don't get it recharged promptly, they're not going to last long at all. You can ruin a set of batteries in 6 months.
But in designing, I guess
Yeah.
the question
Sure.
is, you design something for no more than a 20% discharge, 25, I mean, is there something that's been found to be
Sure.
more practical in the developing world as far as life versus cost?
If I was designing one in the developing world and knew that there was a good chance I wasn't going to get deep cycle, I wouldn't design for more than 20-25% discharge, just
Yeah,
for
that's about
safety. You're going to buy a lot of batteries to do that, but it's going to have a better chance of living. All right, that's all the time we had. We appreciate you coming.
Thank you so
Hopefully
much.
it's been interesting.